Hi everyone, Mr. Allen here. Just thought I should maybe run through standard deviation in this next section. There's a couple of things here that people sometimes have trouble with, and initially it's really just kind of the formula, quote unquote, is kind of scary looking. So just a quick definition in case you've forgotten or don't know for some reason. Absolute value, when you see this symbol, sort of two lines around a value, it's asking you to deal with the size of the value, the positive of the value. So without worrying about the little math explanation here, pretty straightforward stuff. 5 becomes positive 5, negative 15. The size of that, the distance it is from 0 is 15. Some calculation here that works out to negative 16. Again, distance from 0, the size of it is 16. Deviation basically talks about how far are we off. In this case, the mean is what we're going to be looking at. And just a quick note on sort of well, I guess I'll come right here, the two variance formulas. Now we've seen this before, an n minus 1 for a sample and a big capital N for a population, an x bar for mean here and a mu for mean here. I understand that these two formulas are essentially the same, as was the previous one we saw, which was doing averages or means for populations and samples. We won't worry too much about which one. If I tell you in a question that we're dealing with a sample, then you should know that you divide by n minus 1. If you know for sure it's a population, divide by n, so the size of the entire group, or the size of the group minus 1. But for the most part, that's not going to be a big issue. And again, unless it's super obvious in the question, I probably won't even worry about which one you choose to do. And quick explanation here as to why n minus 1 versus n. And so, the reading here maybe isn't super clear, but essentially what it says is, if I look at, and I'll jump here for now, pick a different group. If I look at a group like this, now, if this is supposed to be my actual population, and obviously it's too small to be a population that I would take a sample from, but if this were my entire population, you want to recognize that a lot of the numbers are clustered together here in the middle, something around what will become our mean. A few values are off in the extremes. And so the thinking here is, if I'm looking at a sample group instead of an entire population, the chances are I'm much more likely to miss those kind of unique, those outliers, those values that are kind of way out to the one side or way out to the other side. I'm more likely to miss those than the values that are more popular and more common. And so by dealing with n minus 1, so instead of dividing by 10 items, I divide by 9. Instead of dividing by the 100 items in my sample, I divide by 99. We actually just increase the value that we're calculating, so that we're sort of compensating for the fact that we're likely to have missed those kind of extreme values that would make a bigger difference. So again, not the biggest deal in the world, but understand that if the question tells you you're looking at a sample of something, I will expect you to divide by n minus 1, the size of the group minus 1 item. If you know it's a population, you should divide by the entire thing. And if it's unclear, then we'll accept either one, unless it's, again, very obvious in the question, in the context of the question. Standard deviation is the square root of the variance. Sorry, I didn't finish up here. And so what this formula is asking me to do, and again, I know it's kind of scary looking when you see it written mathematically. It's saying calculate the mean, either as x bar or mu, as the case may be, and then subtract the mean from each of the various pieces of data that we have. Square that result and add them all up. Okay, so again, kind of strange looking, scary looking, but if we come down here to an actual example, here is the data that we're working with. And I don't know if it actually says, or if we just, so we find the average or the mean in the group to be the 67. And then take each individual item, each individual member of the group and subtract the 67. So 70 minus 67 and square it. Add to that 62 minus 67 and square it. Add to that the 59 and so on. So you can see that the math behind doing this calculation is actually pretty easy. It does take some time, but as far as complexity goes, there isn't much there. The idea here is we're looking at this as if it's the entire population and the entire history of this company. So we're dividing by the 6 because there are 1, 2, 3, 4, 5, 6 items in the group, and we come up with a variance of 25.3. Now, just so you know, variance is rarely something we'll be using other than because it leads us to standard deviation. The standard deviation, and again, denoted by a funny little symbol here, is going to be the square root of that variance value. And so what that means, and sort of what's important here, is to understand what this is telling me is this is the amount that in general my stock bounces around the mean. So in this case, the mean is usually somewhere between 67 plus or minus $5. So something like 62 to 72 seems to be the trend that we're looking at this point. Now I'm going to flip back over here. So just kind of looking at a bit of data here. These are assumedly test marks for our class, or for a class, let's say. It doesn't have to be ours. These are not legitimate numbers. I made them up. Standard deviation becomes a way for us to judge our mean. So if you look at these numbers, I've calculated the mean, I've calculated the median. I left the mode in there for no good reason because mode is kind of useless a lot of the time. The mean of 81 seems pretty reasonable for this group. It matches up with the median fairly nicely, and you can sort of see that looking at the values, obviously some are a fair bit lower and a fair bit higher, but it does seem to make perfect sense. My standard deviations, depending on which one I'm calculating, if this is a sample, 8.06. If this is the entire population, then 7.7. And you can see that they're not going to be very far off. But there's sort of, we give ourselves that little bit extra leeway with the sample, just saying that we could have missed some extreme values that would make a big difference. So what this is telling me is that my mean is pretty accurate because in general, most things are within 8 marks. Most of the marks in the class are within 8 marks of the 81. So, 73 up to about 89 covers, well, obviously, the vast majority of the marks. So that in this case, a lowish standard deviation indicates that the mean is pretty accurate. Going a little further, of course, if the marks kind of bounce around a little bit more, we have some lower marks down here. My mean is now 72, but my standard deviation is up to 19, meaning that the majority of the marks are in this kind of 72 minus almost 20, so down to about 50, so anywhere from about 52 up to about 92 is sort of where the biggest group of my population is. And so the mean really isn't quite as reflective of the actual values anymore. And then sort of if we take it to a little bit more of an extreme, we've got some zeros, either people skipped or actually got 0, I suppose. You can sort of see that overall the people who wrote the test, other than maybe 1 or 2 people, did extremely well, and they did fairly well as well. A mean of 67, so this is suggesting that my class average is 67. And kind of if you look at just what's happened here, it should be pretty clear that really everybody who wrote the test and made what would be considered probably a normal or a decent attempt at it did better than the 67. So the 67 really is not a good indication of this information. Without standard deviation, maybe we wouldn't recognize that. This is why, just sort of as an aside, median is what shows up on your report cards, because even though we have sort of 3 zeros here, the median is a decent reflection overall of how people have done. Assumedly, if these people wrote the test and did poorly, oops, assuming if they weren't showing up very often, they might have done poorly on the test anyways. You can see the mean changed considerably because of the addition of new marks here. The median didn't change at all, and the standard deviation, of course, came down quite a bit. So the idea is that the standard deviation allows me to get a feel for how good my mean is. In this case, my mean is pretty bad because I'm saying the mean is 67, but I could be off by as much as about 37, generally speaking. So that's kind of standard deviation. Again, the formula can be scary. There are multiple examples here of just displaying the data in different formats and kind of going about figuring out what's the standard deviation based on the reading of the table. But these ones are not really, it's not a new calculation. It's just sort of getting an understanding of how to read the tables and then pull the data from them. So in this one, calculating the means again, going through the calculations. It lets you do the second one yourself. Frequency table, we've sort of seen these enough times now. This means that one time there was a 20, 4 times there was 25. So essentially it's telling me if I was going to do an average here or a mean here, I'm doing 20 plus 25 plus 25 plus 25 plus 25 plus 35. And so when we go about calculating the frequency, they're sort of showing it as if it's a new calculation again, and I don't necessarily like that. I could have maybe taken that out. But basically it means there's one of these, so we'd have to do this one time. There are 4 of these, so we'd have to do this 4 times. And instead of doing 25 minus the mean squared plus 25 minus the mean squared and so on, of course, we can just do 4 times that calculation. The 0, of course, can be left out, and then there's 1 of each of the other 2.